To begin, let's ask a simple question. What is light? Well, that's easy. Light is an electromagnetic wave. But just what exactly is an electromagnetic wave? In this video, I'm going to answer this question intuitively, visually, and without complicated formulae or equations. An electromagnetic wave is simply a change in the electric and magnetic fields. The electric and magnetic fields are intricately linked such that a change in one field immediately induces a change in the other. Therefore, an electromagnetic wave can be created by introducing a change in either the electric field or the magnetic field. Before we continue, let's quickly go over what a magnetic field is. Every magnet has an invisible field surrounding it, in which the magnet can affect matter. We can describe the magnetic field of a bar magnet using magnetic field lines, which extend out of the north pole of the magnet, form a loop around the magnet, and then enter the magnet from its south pole. The field lines have a direction. Outside the magnet, the field lines point towards the south pole of the magnet, while inside the magnet, the field lines point towards the north pole. We can indicate the direction of the field by drawing arrows on the field lines. The magnetic field actually has infinite extent. However, its strength, that is, the force that the magnet can exert on matter, decreases rapidly with distance. This means the further away you are from a magnet, the less it can affect you. You can see that the magnetic field of a bar magnet is quite complicated. There's a lot going on and a lot of field lines to keep track of. We'll be using a simpler magnetic field, the field produced by an electric current, to demonstrate electromagnetic waves. An electric current creates a magnetic field around the wire it is flowing in. The field lines form rings around the wire, with the direction of the lines given by the right-hand rule. When the thumb of the right hand is oriented in the direction of the current, the magnetic field is oriented in the direction that the rest of the fingers are pointing in, which notice are curled in a cylinder around the wire. This is known as Ampere's law. This means if we place a wire perpendicular to the screen, when the current is flowing towards the screen, the magnetic field is oriented in a clockwise direction. On the other hand, when the current is flowing away from the screen and towards you, the magnetic field is oriented in a counterclockwise direction. This may seem complicated, but this field is actually simpler than the field of the bar magnet that we're all familiar with. The magnetic field of a bar magnet has two loops oriented in opposite directions on both sides of the magnet, whereas a current in a straight wire only produces a magnetic field with a single loop. Notice that the loops on the right side of the magnet point clockwise when the north pole is facing upwards and point counterclockwise when the north pole is facing downwards. You can think of changing the direction of a magnetic field as rotating a magnet by 180 degrees. To simplify things even further, we'll represent the field lines by drawing an arrow at each point in space that points in the same direction as the nearest field line. Instead of a series of continuous parallel field lines, we have a grid of arrows, which is easier to work with. The size of each arrow indicates the strength of the field at that point, with a larger arrow indicating a stronger field. This construction is known as a vector field, which we'll discuss in more detail in a future video. Right now, what you're seeing is a constant, that is non-changing, magnetic field. We can still clearly see the loops around the wire even though we've removed the field lines. The loops are going clockwise, which indicates that the current in the wire is flowing towards the screen. Now let's change the direction of the field, which in reality we can do by changing the direction of the current in the wire. Notice that the arrows are now pointing counterclockwise. Nothing surprising yet. However, notice that the arrows didn't all change their direction at once. The arrows closer to the wire change their direction before the arrows further away from the wire. In fact, you can see the change in direction of the arrows traveling outwards in a circle away from the wire. Let's change the direction of the field again and keep a close eye on the arrows. Once again, the arrows change direction with the change traveling outwards. In fact, this traveling change resembles a wave in the magnetic field. Remember that a change in the magnetic field also induces a change in the electric field and vice versa. This means at each point where the magnetic field is changing, there is a corresponding change in the electric field that is perpendicular to the magnetic field. In this demonstration, the electric field is perpendicular to the screen and points in the direction in which the current is flowing in the wire, which is now shown in red. Notice you can see a wave in the electric field as well. When both the magnetic and electric fields are shown, you can see that the waves in the two fields are aligned together. It is this pair of waves that is referred to as an electromagnetic wave. With both fields shown, the demonstration is quite cluttered. So let's hide the electric field for now to make the demonstration easier to understand. Just remember, there is a changing electric field perpendicular to the magnetic field. Now let's change the direction of the field at regular intervals. Notice we can see bands where the arrows are aligned traveling outwards from the wire. The direction of the arrows flips between alternating bands. These bands travel outwards at a constant velocity, which is referred to as the speed of light. The bands radiate outwards away from the wire, and hence why electromagnetic waves are also referred to as radiation. Notice something else about the bands? Let's compare the size of the arrows now to the size of the corresponding arrows at the beginning before we started changing the direction of the field. Notice that the arrows towards the edges are larger now when the field is changing than they were at the start, when the field wasn't changing. Remember that the size of the arrows indicates the strength of the field at each point. This means a changing magnetic field decays much more gradually than a constant magnetic field, which in turn means that an electromagnetic wave can affect matter at a much greater distance. In fact, if we look closely, we can see that the field inside the traveling bands doesn't actually decay. However, as the bands grow in diameter, the energy of the field spreads out over a larger area. As a result, the arrows do get smaller the further away we are from the source of the electromagnetic wave. This is why a flashlight gets dimmer the further away you are from it. So now that we have an intuitive idea of what electromagnetic waves are and how they are created, the question is, what can these waves actually do? We've already mentioned that electromagnetic waves can affect matter far from the source of the waves. The changing electric and magnetic fields can accelerate charged particles, such as electrons. The direction in which the particles are accelerated depends on the direction of the field, and the amount by which they are accelerated depends on the field's strength. This means electromagnetic waves can induce electrical currents in conductors, since they contain a large number of electrons that are accelerated at once. In fact, this is how antennas convert radio waves into electrical signals. This also works in reverse. An accelerated charged particle produces an electromagnetic wave, which is what we've been demonstrating throughout this video. Because of this ability to accelerate charged particles, electromagnetic waves carry energy. Now let's look at some of the properties of electromagnetic waves. The amplitude of the wave is the strength of the electromagnetic field, which is depicted by the size of the arrows. The stronger the field, the greater the effect that the wave will have on matter. The amplitude also indicates the power of the wave. A wave with a large amplitude carries more power than a wave with a smaller amplitude. For visible light, we perceive the amplitude as the brightness of the light. The frequency of an electromagnetic wave measured in hertz is the number of times the direction of the field changes per second. Related to the frequency is the wavelength, which is the distance between two adjacent peaks or valleys in a wave, or in other words, the width of the traveling bands. The wavelength is inversely proportional to the frequency, which means the higher the frequency, the shorter the wavelength. We can observe the traveling bands getting narrower as we start changing the direction of the field more frequently. Different frequencies of electromagnetic waves have different effects on matter, which gives rise to the electromagnetic spectrum. On the low end of the spectrum, we have radio waves and microwaves that we use for communication. Then we have infrared, which is emitted by atoms when they move around in materials. The more heat a material has, the more the atoms move around and the more infrared radiation they emit. Following infrared, we have visible light, which is the only part of the electromagnetic spectrum that we can directly perceive with our eyes. This part is further subdivided into the colors of the rainbow, where different frequencies of light are perceived as different colors. The lowest frequency of visible light is perceived as red, while the highest frequency is perceived as violet. On the high end of the spectrum, we have ultraviolet light, X-rays and gamma rays, which are referred to as ionizing radiation, because at these frequencies electromagnetic waves have enough energy to knock electrons out of atoms. This makes ionizing radiation dangerous because it can damage DNA by breaking the chemical bonds between the DNA molecules. This leads to an interesting and rather counterintuitive observation that high-frequency electromagnetic waves carry more energy than low-frequency waves, regardless of their amplitude. This phenomenon will be explained in the next video, which will be about photons. To end off, we can now answer the question, what is light? Light is a change in the electromagnetic field that we can detect with our eyes. We can only see a limited range of frequencies directly. Most electromagnetic waves are completely invisible to us, but they still have an effect on matter nevertheless. Thank you for watching. If you found this video interesting, please consider subscribing to the channel so that you don't miss the next video.